I don't know if it's allowed from a Longhorn, but howdy. Okay, CFRP, carbon fiber reinforced polymers. The reason I'm presenting on this today is because there has been a lot of heightened interest, not just from us in the bridge division, but also from producers and contractors and from the districts. I think it's gotten a lot of attention the last few years, and a lot of times this is the kind of technology that we really have to push on people. This is one that it's really not the case. This is one that people are really coming to us and asking us about opportunities for using it. So a lot of heightened interest, a lot of increased use, which I think is a good thing for everybody. We were actually caught a little off guard in the last year and a half or so as producers began approaching us because we hadn't really significantly increased our use of the CFRP, but suddenly there was a lot more interest, and so that we kind of opened our eyes and realized that there was a lot of potential for this. So we've done a lot of work in the last year or so on CFRP, and we are ready for implementation. So we have used CFRP for some time now, but really for the most part in confinement of concrete members, and those were typically in applications where we had done concrete repair and we wanted to hold that patch material in place. There had been other applications where we did use for some structural upgrades or strengthening to account for reduced capacity, but really what we've done up to now is hold patch material in place. And moving forward, what we address in the new spec and our new DMS is an option for CFRP for strengthening as opposed to just confinement. We're looking to increase capacity, and in a lot of cases we're looking to restore capacity either as a result from a deterioration due to age or even more often vehicular impact or fire damage. The ACI guidelines have been in place for some time, since the early 2000s, so over 10 years now. ACI has had some equations. Other parts of the country jumped on it a little earlier than we did. We were a little skeptical about the potential for increasing capacity, so we've slowed down a little bit, and we did some research of our own, but we are ready to move forward, and I'll touch on that research a little later. Okay, where we are, the 2014 standard specs. Hopefully most of you have had an opportunity to hear us present on that in the last couple of months, but the special specification 4191 has been in place for a long time. We rolled that in, and so now it will become a standard spec item. 786, I think. Hopefully, again, most of you are aware the draft version of the new spec is available online, so you can go to our website and see that, and the final version should be coming out in the very, very near future, and the CFRP will be a part of that. One of the things that we changed in the spec when we transferred it over from the special spec was very specific requirements for training of the installers, and this is something that the manufacturers of the CFRP really address a lot on their own. They don't want unqualified personnel installing their material because it makes them look really bad when it fails, and CFRP is certainly one of those materials that you have to install properly. So there's a very good training program in place from all of our approved suppliers, and that really has an additional side benefit that it's kind of a cutter when it comes to our bidders. It ensures that only really qualified contractors are going to be getting our jobs in these kinds of rehabilitation scenarios. It also includes a lot of detailed surface prep, installation, and testing requirements. You'll see in the new spec references all over the place to the new concrete repair manual. Most of the concrete repair will be addressed in the manual. The CFRP is not one of them. There are a few items that we left in the spec with detailed installation requirements. So really everything you need to know about the CFRP installation will be included in that standard spec item 786. As I already brought up, there will be two categories, very specific requirements for each. If we're talking about just protection, and we went back and forth about what to call this, protection really also means confinement. So when we say protection, it's what we've used in the past to term confinement. We don't have as strict requirements because we're not looking for strengthening in that case, but we do still have some requirements, some minimum requirements for capacity on those. And then for the strengthening, it is a little harder to meet that. Something that changed a little bit when we were bringing this up a couple of years ago, talking about strengthening, we initially offered to the AGC that we would do the calculations for the CFRP, and we quickly realized that that was a problem because the varying suppliers have their own equations and capacities. So really what we would have had to have done is take one of the suppliers, done a design based on their material, and then put it in the rehab documents, and that wouldn't have been fair to the other suppliers. So what we have decided on is, as opposed to doing the design ourselves, we will give the contractor what the required increase in shear or flexural capacity is, and then we require that they give us signed and sealed documents from an engineer based on whichever manufacturer they select for the CFRP to ensure that they are able to meet that additional capacity. Pre-approved materials only. I'll touch on the one specifically for CFRP, but I want to talk about that in general for a moment. Our construction division does a great job maintaining these pre-approved lists, and really critical that not just for CFRP, but for all materials out there. Whenever we have DMS, departmental material specifications and corresponding material producer lists, that we really enforce those and the contractors use pre-approved lists. We still, unfortunately, quite frequently see unapproved materials make their ways out to the bridges, and it doesn't matter how good a job you do installing. If the material's no good, it's not going to be effective. So please take a look at that. Whenever there's an MPL available, please enforce that and make sure the contractor is using pre-approved materials. So the pre-approved list for CFRP, we haven't used it a whole lot up to now, and so Bridge Division, our group, maintained kind of an unofficial list of the suppliers, and those were Sika, Fife, and BASF. As I noted, we've had a lot of other producers approach us recently, and we have, in the last couple of months, added Dow and Simpson Strong-Tie to the list, and we've got a couple of others that have approached us as well, so we'll continue looking at those. We've written a DMS for this. It's really, with the increased use, it's not appropriate for us to be maintaining this kind of unofficial list anymore, so we did want a DMS with very specific requirements for the suppliers. It's done now. When I put this presentation in last Thursday, I said it was almost ready. It actually is ready now. I think probably some of you hopefully saw the DMS 4700 go out on Friday for review, so if you do have any comments, by all means get those back to me. Our intention is to have this DMS in place in the next month or so. At that point, the construction division will maintain the material producer list like they do for all the DMSs. It does include the two categories as outlined in the spec, one for protection or confinement, and then one for strengthening. For now, we are going to accept independent lab results. There was a lot of back and forth between us and CST about how best to do that, but there are some pretty unique testing requirements in here. So for now, we are going to allow the suppliers to give us their own independent lab results, and we're going to go on that. If we find that there's a problem with that moving forward, we may end up having to do our own testing. Okay, so what we have done up to now, unfortunately that photo is something that could be taken from anywhere around the state. Our bridges are getting hit very, very, very frequently, especially with the increase in the energy sector work. These trucks are smacking our bridges left and right. So these are the kinds of, this is the kind of damage we respond to on a nearly weekly basis now. We do see a lot of cases where strands are severed and significantly reduced capacity, and these are things that we have to move on quickly. If you want to replace the beam, then you're talking about serious disruption to traffic. So CFRP offers a really good alternative to that, where we can sometimes replace the strands, or splice the strands, excuse me, and then patch, and then we can actually increase capacity of the CFRP. So we're talking about a day or two of work with very little disruption to traffic, as opposed to taking out a chunk of the bridge and replacing it. It does only make up for the ultimate strength, but in most cases that's fine. We have so much redundancy with our pre-stress girders. We're comfortable a lot of times if we have reduced capacity in one or two, as long as the overall composite section of the bridge is okay. The CFRP dramatically increases ductility, and I'll show a couple of photos of that a little bit later in the presentation. And it offers some sacrificial reinforcing in the lateral direction. And again, some other photos will show that. So here's a very typical application. This is something that we do a lot of now. So the beam gets hit, the beam gets patched, and then we put the CFRP over it. And not only does it increase capacity, unfortunately a lot of our concrete patches don't last very long, especially if beams get hit again, and it poses a real hazard to traffic if we're dropping chunks of concrete onto them. So something that the CFRP works very well for is holding patch material in place. So in addition to the strengthening, it's a very good safeguard to make sure we're not dropping concrete onto passing vehicles. The finished product, you can hardly even see it's there. This is the CFRP can be painted. Typically you can find a paint that very closely resembles the surrounding concrete, and it ends up looking very nice at the end, which has other implications on non-standard bridges for aesthetic purposes. But you can see a little bit, but really effective there with the CFRP matching the existing concrete. This is something that one of our larger district maintenance crews did fairly recently. They were able to come in and do this work themselves. You see that mangled exterior girder there. They came in and did some strand splices, then did their concrete patching, put the CFRP in, and again, very nice looking finished product there. Nasty truck impact here, unfortunately, and this is something where there, again, is a very good structural application for the CFRP as opposed to coming in and doing a partial bridge replacement, or in this case, it would have been probably a total bridge replacement. We're able to come in, do some concrete work on the column, inject some cracks, and then wrap it with the CFRP, and there's your finished column there. Very, very quick and very safe. We're confident in this system at the end that we do have sufficient capacity for continued use. Distributing impact loads and stresses. So a little over a year ago, Amy and John ditched the old metal bridge protection assemblies on the exterior girders. We found that they, in a lot of cases, were not very effective at distributing the loads like we wanted, and we have replaced the old BPAs with the CFRP. So that is now on the standards for all the pre-stressed girder shapes to have CFRP, where in the past you would have had the bridge protection assemblies. And we find that when these bridges do take a hit and the CFRP is in place, they do an excellent job of distributing the stress, spreading out that load, and then again, holding that damaged concrete in place as opposed to dumping it on the road under the bridge. This was a big CFRP project a couple of years ago. This is unfortunately our most famous ASR example in the state. This is OH Ivy. You guys have probably seen these photos from me in past presentations. I presented on ASR here a couple of years ago. We thought we'd be real smart in 2004 and do a checkerboard pattern, and the idea behind that was we wanted to see if further deterioration was occurring. So we had this checkerboard pattern so we could see what happened, and what we saw was it kept cracking, so we had to go back in 2012 and just end up wrapping the whole thing anyway. So this was a very successful project implemented by Gibson in 2012, very large-scale application, and went very, very well, I thought. And you can see this is prior to painting, but did it on all the columns. Each one of these columns was exhibiting some pretty significant alkali silica reaction expansion, and so what we were counting on from the CFRP is to confine that concrete material, stop the expansion of that concrete, and hopefully get a few more decades of use out of this bridge, which we would not have gotten had we not been able to do this. Fire damage. This is another really good opportunity to use FRP. Very badly fire damaged structure here. Again, you're looking at, without CFRP, probably large-scale replacement of the structure, but instead we were able to go in and do some concrete patching. And you can see, obviously, that the fire did get to the reinforcement. Concrete does great in fires as long as the fire doesn't actually reach the steel. As soon as the fire reaches the steel, then you do have the potential for significantly reduced capacity. So in this case, we weren't just looking for confinement, we were looking for strengthening. So we put FRP on the beams to increase the shear strength, and then in the columns for confinement. We also beefed up those caps significantly. That's obviously not original. That's a lot beefier than it was before we got to it. Okay, so what we are doing is addressing concrete, some other, I think there's possibility for going to steel, but it's not something we're looking at right now. Different types of FRP, there's carbon fiber reinforced polymer and glass fiber reinforced polymer. The carbon is much stronger than the glass, and when we were preparing the spec and the DMS, we were actually looking at having two categories, but what we found now is that the glass is essentially just as expensive as a carbon, so really not much use to use it. So we just decided to go all carbon. If that changes in the future and the glass does become less expensive, then we may go back and look at that as an option in confinement or protection only applications. All right, this is a biggie, TxDOT historic considerations. We work with the Texas Historic Commission a lot, and I think that there's a real opportunity with the FRP to address deterioration in historic structures, or in the cases of low capacity, we can actually increase capacity and continue use of these bridges. In the past, THC has frowned on the use of CFRP just because they don't like us covering the surface, but we've been meeting with them lately, and I think they recognize the benefits in this. So what CFRP does do for us, it gives us a uniform finish, as I showed you in those previous photos. A big problem we have on historic rehab projects, it's impossible to get patch material to match surrounding concrete. We get specific requests for it all the time, and this is from when I was a consultant or TxDOT. Anytime the owners want concrete patch material that matches the existing concrete, and it just doesn't happen. It's really impossible to achieve. I think the CFRP offers a far more palatable option from an aesthetic standpoint than concrete patching. One potential disadvantage, as I mentioned on the OHIV project, the reason we went with that checkerboard pattern in 2004 is because we wanted to see what was happening after we applied the CFRP. In applications where you cover everything, there's a potential for damage occurring under the wraps that you're not going to be able to see. But really, I think that is, I don't think that that's a significant roadblock. I think Fort Worth is probably tired of seeing this photo show up in our presentations. We use it for a variety of reasons, but you can see there what happens when you do a lot of patching, and you can see how it works. This wasn't anything that the contractor did wrong. This is just how it is. Patch material does not match surrounding concrete. And this is what I was talking about, that there is a CFRP there, and you can see that some corrosion obviously continued in the reinforcement, and it's now starting to come out of the wrap. So we've got something going on under that CFRP that we would have to address. So I think overall it's a minor issue. I think this is going to be rare that this kind of thing happens. Okay, in historic applications, this is maybe not such a good example. We do pull test on the FRP, and this was not a very good job. Obviously, coming back and patching afterwards, that kind of sticks out like a sore thumb. So this is not what we will be looking for when we are patching our pull test. Applications on historic structures. A lot of our older bridges obviously were not designed for current traffic levels, and so there is a need to increase their capacity. Also, there's definitely a need to restore capacity in applications where deterioration has led to reduced capacity as a result of concrete spalling or corrosion of the reinforcement. So addressing this from an aesthetic standpoint, I've already showed you applications where it can be painted, and I think very closely matches surrounding concrete. Our preference in historic applications is actually to use what we call silicone resin paint. It actually mimics concrete. It's got that kind of bumpy surface. We think it looks great. We were a little surprised that the THC has actually come back and asked us in most cases not to use that. I don't think the historic folks really like it when we pretend and try to make something look like it's not. So their preference at this point is actually to stick with the paint. We'll see what happens moving forward. The paint is actually far less expensive than the silicone resin, so maybe it's a good thing. It does offer another benefit. We would be able to clean the bridges. The historic people get nervous a lot of times when we talk about pressure washing the structures because contractors can get a little carried away and do some damage. With the FRP in place, it will be easier to keep these historic structures clean. Long lasting, I like this bullet. We don't have the history, but we're confident it's going to last a long time, I guess because we don't really have any reason to think it's not going to. But there has been some CFRP in place for upwards of 15, 20 years, and it's performing just fine. So we do think that this is a long-lasting repair. We don't think that this is a 5 or 10-year repair. We did meet very recently with the Historic Commission. They had us participate in a panel discussion, and there was a lot of resistance. Again, the historic folks don't like it when we cover stuff up, and that's the whole idea of the FRP, is we are covering stuff up. I think they do recognize that this is a very good benefit if we're talking about significant concrete removal and replacement, or even total bridge rehab or replacement. If that's what we're facing and FRP can help keep us from doing that, then they're very receptive to the idea. I think THC gets kind of a bad rap, sometimes being stubborn and digging their heels in. We've actually found them to be fairly reasonable to work with, and we can go to them and on a case-by-case basis pretty typically get on the same page with them. So they've been very cooperative with us, and we haven't had the kinds of problems that a lot of times you hear about. Obviously, the preference is still to leave the existing surfaces exposed where possible, so of course we'll do that, but the FRP does offer a good alternative in cases where we are having to remove a large amount of concrete. This was an old application. I don't think this is how we would do it today. This is for strengthening of a pan girder bridge, and it looks like we just were placing these ribbons on it. Actually, the strengthening came from the strips going along there, and then the U-shapes are there primarily to hold that strip in place. So there's been a learning curve. I think this is probably effective. I think we could probably do it a little bit better now. Okay, historic bridge application, TxDOT's first application. This is the kind of thing that we nerds get very excited about. We do have our first bridge, older bridge. It's not a historic structure, but I don't know if Rex is here, but we're doing a bridge in South Texas. There he is. We're increasing shear capacity on some variable depth concrete arch beams, and we're doing a new anchored CFRP system, which I will talk about in just a couple of minutes. These are going to be hard to see. I'm just going to go quickly through, but you can see the configuration of the bridge. It's variable depth concrete beams, and we saw some very significant shear cracks in these. And if you want to make a structural engineer nervous, show them shear cracks or shear cracks in an old structure. Very hard to recover from. CFRP, I think, does great in increasing shear capacity. So this was a perfect application for it. I don't know if Dr. Du is in the audience, but he put these plans together, and we are getting ready for implementation. Okay, I got to speed it up here. So the ACI equations I mentioned have been in place for quite a while. Something I want to point out there, this equation, you see that 1.1 factor for dead load. Really what we want to ensure when we do account for CFRP and strengthening is that the bridge will still stand up if the FRP completely fails. And one of the reasons for that is because the FRP does not stand up well to fire damage, and there is a potential for debonding and failure. So we want to make sure that if there's a complete failure of the FRP, the bridge isn't going to come down. So the bridge has to have minimum capacity before you even consider strengthening with the FRP. This one was kind of funny. We've seen cases where flexural capacity was increased by 160%. We didn't do that. Another DOT did it. Just because you can do that doesn't mean you should. We haven't really decided on a cap yet for what we think is appropriate for increasing capacity, but we're leaning to somewhere around 40%. In all likelihood, it's going to be kind of a case-by-case basis. We'll deem each bridge individually and determine what's appropriate. Okay, our good friends at the University of Texas at Austin did some research for us recently, and this was based on a lot of it was based on the bonded FRP, and they came up with their own system as well. In addition to the ACI testing, they actually bonded the FRP to the concrete, and we saw very dramatic increases in its effectiveness and strength. And I'll show you a couple of side-by-side photos here in a second. They did provide us some new equations. I think that we have validated the ACI equations up to this point enough to be confident to use them. University of Texas has given us new equations that we can use in some cases where we do need a dramatic increase in shear capacity by anchoring the FRP. And the way you do it, it looks hokey. I mean, you wouldn't believe how much this works, but it really is just taking strips of the wrap. I mean, it looks like an arts and crafts project that my kids would do, but you just fan it out. You drill a hole like what he's doing here, and you shove this part in and you fan it out, and it really doesn't look like much, but it very, very dramatically increases the effectiveness of this FRP by making it composite with the concrete that you're attaching it to. And what you see there is this is FRP bonded in accordance with the ACI requirements, and you can see the failure actually occurs through the wrap. Here, this is the one with those fans in place, and the concrete basically just exploded under shear testing. So a very, very dramatic increase. And it's not that hard to install either. The project I showed you, Arroyo Burro, for Rex, we're doing that fanned option because we do think that it's going to dramatically increase. Let me see. Do we have the... Yeah, so Tanya, one of our drafters, put this really nice looking isometric detail together, and this shows the requirement for the fan application. And again, you can see here, it wasn't the wraps that failed under the shear testing. The entire block of concrete came out outside of the reinforcing cage. So good stuff. That's all I have. Anybody have any questions? Okay, thanks.